Hello, and welcome to this Eureka webinar in association with Maxon. Today's webinar is entitled Using DC Motors Underwater is More Challenging Than on Mars, and is presented by Andrew Gibson, Maxon's Subsea Sales Engineer. Before I hand over to Andrew, I should just say that if you have any questions during the presentation, please type them into the box on the right-hand side of your screen, and we'll attempt to answer them at the end. If we don't have time to answer them at the end, we will hand them on to Maxon and they will answer them for you offline. And with that, it just remains for me to hand over to Andrew. Andrew.
Thank you, Paul. Hello, everyone. Thank you for joining us today. As Paul mentioned, my name's Andrew Gibson. I'm the Subsea Sales Engineer for Maxon in the UK. We have a wider global team who are working in the subsea arena, so we contact each other. We share our experiences, challenges, and things like that. So we get to know what else is happening around the globe with sort of other countries in the subsea arena. So that all links in and gives us a strong team globally. So as Paul mentioned, I'm going to talk to you about why using DC motors underwater is more challenging on Mars. I think a lot of people know Maxon has quite a heritage of using our products on Mars exploration missions. So not a lot of people know about what we're doing in the subsea arena and the challenges associated with that. I'll just turn my camera off so you can see the slides clearly. So before we get into the guts of sort of the subsea, a quick introduction to Maxon for those who don't know us. We're a privately owned business and we're headquartered in central Switzerland. We've got over 3,000 employees globally, and we're turning around in the region of around £600 million per annum. We manufacture over 5 million motor-based products annually, so that's over 20,000 motors every day. So we've got quite a high volume of product coming through our factories. So within the business, we've got all our own design for motors. We've got our design for sensors and motor control and gearboxes as well. So we manufacture predominantly in-house. We do use supply chain, but sort of the key competences we keep in-house. So manufacturing the motors, the gearboxes, and the encoders. We've got quite a suite of manufacturing, which does include injection molding. So we've got polymer parts for some of the motors that we manufacture ourselves in-house. But what a lot of people don't know is in Germany, we've got ceramic injection molding and metal injection molding as well. So how to work with Maxon? So we split it into these three categories really. So we have a catalogue, 500 plus pages of product, which includes all the motors, the gearboxes, encoders, controllers, and what we call our sort of Maxon products. So in each page we can pair up with motors, with different gearboxes, with different sensors. So it's all easy to use in the catalogue. So it's all there. We can create quite a wide range of products. So in the last slide, I said we're manufacturing over 20,000 motor-based products a day. So only 20% of that product falls in this first category as direct, as seen in the catalogue. 80% falls into the other two categories. So we'll move on to the next one, which is what we class as semi-customized products. So we take the standard motor gearbox sensor combinations, and our customers ask for some specific modifications. Some of those modifications can be relatively simple. It might be an extra flat on a shaft, it might be shorter cables, longer cables, but they can get more and more complex. So special flanges and things like that. Which then moves on to sort of our larger projects, which is the fully customized products, where we work with our customers and we're providing a more bespoke solution. but it's very cost effective because we're using the sort of the guts of what we have, sort of motor windings, magnets, gears that we manufacture in volume. So we can build up these quite highly customized products, very very cost effective for our customers. We work in some quite challenging environments, which leads us on to why we've got the quality assurances across the bottom there. So everything that leaves the factory as standard is ISO 9001, and you as our customers wouldn't expect anything less. But we've also got EN 9100, which covers us for our aerospace product lines, and we've got ISO 13485, which covers for medical devices. We've also got the environmental quality standard, the ISO 14001. So getting on to what we're talking about today. So what's we're talking about the subsea arena. So what's happening underneath the waves? We look out from the shores of this country. We might see a wind farm, offshore wind farm, or we might see an oil rig in the distance. And we see that, but it's what's happening below the waves that's really important, and there's probably a lot more going on than what most people realise. So you've got the oil rig there, and that drills down into the well, and once they've reached the oil well, then they place what you can see there on the seabed, sort of. It's a valve system to put on the cap of the well to allow them to sort of open and close valves, the flow of oil into the pipelines to get the oil to shore. These are called Christmas trees for those in the subsea arena. So those sit on the seabed, and so they have pipelines connected to them. So the oil can be transferred to shore. And then, in support of all this, you've got the remotely operated vehicles and autonomous underwater vehicles. So, the remote operated vehicles, they come down, they're operating the valves on the Christmas trees, they're directing the oil to which pipeline they want it to go into to get to which refinery where onshore. But they're also, they're looking at, sort of preventative maintenance as well. So, we're looking at the integrity of the pipelines, of the Christmas trees, of the structures of the wells, making sure that nothing's corroding beyond what it should be doing. So it's really, sort of when you see an oil rig, it's quite busy below the surface. And, thinking now on the sort of the more modern, renewables and the offshore wind farms, it's going to be much the same below the wind farms as well. So you've got the structure of the wind turbine down to the seabed. So that needs to be monitored, and then sort of the cables then will go into a sort of a single single cable then to come to shore. So we don't want to run a cable from every wind turbine. So there's some form of sort of consolidation of all the power from the different wind turbines, and then it'll just get brought to shore. So why is subsea more challenging than Mars? I think it's widely spoken about within the scientific communities that we do know more about the surfaces of the Moon and Mars than we do of our deepest oceans. It really boils down to two reasons as to why it's so challenging. So firstly is pressure. So for every 10 meters below the surface of the sea you go, the pressure increases by 1 bar. So when you get down to 6,000 meters, which isn't deep as far as all our oceans are, you've got a pressure of 600 bar. Now that's 8,700 psi. That's, if you think about that kind of pressure, a standard car tires around 35 psi. That 8,000 psi, that's a lot more than what you're using to create the body panels in the presses for your cars. So that's a serious amount of pressure. So we have to pressure compensate our products or the products for subsea to make sure that the pressure under the sea doesn't crush the products. Because that kind of pressure, it's just literally going to be like grabbing an empty drinks can in your hand and just squeezing it. It will collapse. So we fill our products with oil, and then we have a pressure compensating device. Then, so as the products drop down below the surface of the sea, the oil within the motor then gets the pressure increases as the pressure outside, so it levels it out. And just for comparison as well, we're looking at comparing with Mars. The pressure on Mars is 8 millibars. That's 0.116 psi. So that's absolutely nothing. So it is a massive difference in pressure. The second one is salt water. We all know that salt is corrosive, and salt water is a big problem. So we need to be very careful as to which materials we select. If you have dissimilar metals, the salt water causes a chemical reaction which causes electrolytic corrosion. So this chemical reaction, one of the materials will be eroded away through electrolytic corrosion. So we have to be really careful as to what materials we use. So one of the good materials is titanium. So it has proven to be very good in the subsea environment. So I'll start talking about sort of the products that we've got for this environment. So we'll start with the maxon thrusters. So we've developed a range of thrusters for providing propulsion for underwater vehicles. So these are pressure compensated. So these are proven down to depths of 6,000 meters. So as you can see there, you've got the thruster, then you've got some pipes with oil leading to the pressure compensation device. So these are available in 4 sizes. So we've got the MT, which is maxon thruster, and then 20, 30, 40, 70. So, and then the numbers, like a lot of our products, just relates to the diameter of the body. So we've got 20, 30, 40, 70 millimeter diameter bodies. So each thruster is available in left and right hand propeller options. This is to allow people to put multiple thrusters on a vehicle and then balance out the gyroscopic forces of the rotating propeller. So the thrust levels that we get from these, so starting with the 20 mil diameter body, we're getting around 1.3 kilos, up to the 70 millimeters where we're getting almost 17 kilos of continuous thrust. So the applications for the thrusters. So we've got the remotely operated vehicles, which I mentioned on the initial slide, showing the underwater environment. So these are the traditional vehicles that we've seen for many years. We saw them going down to finding when they found the Titanic and explore around there. So they're connected to the surface by an umbilical. So all the power and the communication comes down through the umbilical cord. So generally, these will have sort of 5, 6, maybe more thrusters on there. So these will be orientated to allow the ROV to move forward, backwards, left, right, up and down. So they're piloted by a person, which is either on the boat above where the umbilical connects to. But more and more now, the pilots are becoming land-based. As the levels of communication become better and better. So it's that the pilots are getting into better environments. So they'll see what's happening. There's the cameras on the ROV, and they've got the arms. So they'll be using joystick controls to maneuver the ROV. And then separate joysticks for the manipulators to carry out what they're trying to do, whether that's operating valves or, as they say, is connecting ropes to a barrel underwater. second type of vehicles is the autonomous underwater vehicles, which is the image on the right. So these are, sort of newer era of vehicles where these will have a programmed mission to carry out. So whether that's following a pipe or a cable on the seabed, scanning, looking for any damages or any issues that could cause problems, or they're used now for sort of seismic scanning as well, so they can scan the rock surface or the structure of the rocks below the seabed. So they'll go around, they'll carry out the mission, and then they'll come back and they'll recharge, they'll download the data, and then upload the data for the next mission. But sort of just coming into the arena now is sort of having docking stations on the seabed. So the AUVs, they'll have the mission, they'll carry out the mission, and then they'll come back into the docking station on the seabed where they'll recharge, they'll download the data and then upload the data as well. So it's making it a lot more easy to carry out these missions without putting people on ships on the ocean. So it's the industry is really working hard to cut the environmental emissions down, and do as much as they can from land-based operations. So we've also developed some subsea actuators. These again are pressure compensated to operate to depths of 6,000 meters. So they're based generally on the thruster housings. So we've got the housing diameters of 20, 30, 40 and 70 millimeters. So like we do with our more traditional products, we've got the housing. So what we can do is when we're looking at a customer application, we can fine tune the motor gearbox combinations to suit the customer's requirements. For speed and torque. So it could be a higher ratio gearbox to for a slower speed and higher torque, or it could be a sort of a lower ratio gearbox for a higher speed, lower torque. We do also available with rotary and linear outputs. So on the image on the right there, you can see that actuator has got the maxon screwdriver product, where we can have a gearbox then with the output being a ball screw or a lead screw. So it's really good product. So the image on the left, this shows that when we're talking about 80% of what we supply is modified to customer specific requirements. So what we've got here is we've got on the bottom side, we've got the motor gearbox in the actuator. And then we also got the inbuilt compensator as well. So this product was developed for a customer. So he's got all in one. Instead of having the compensator and having to mount it, it's already mounted by us. So it's made his life easier. So he can just fit the actuator and not have to worry about mounting his compensator anywhere else. So when we talk about applications for the actuators, what are they used for? So we're looking at things such as inspection scanning systems. So if you look at the image on the left there, we've got an ROV, but on the front of there's a pipeline scanning system for checking for corrosion. So this is a linear actuator then, which is actuating the scanning heads around the pipe to scan for corrosion. And then I've talked about the all-in-one package on the previous slide. So that was used in the tripod there on the image on the right. So this is a leveling mechanism. So this is a seabed-based seismic scanner. So the customer drops a number of these tripods onto the seabed to scan down into the rock formations, searching out the oil wells below the surface and the easiest way to get to those as well, through the softer rock. But the way the scanning head works is it needs to be level, and like land above water, the seabed's not always level. So that unit was used to level these tripods once they were on the seabed. And then sort of we were looking at sort of images of the AUVs as well. A lot of the AUVs have just a one or two thrusters to provide the propulsion, and then they're steered by fins. So the sort of subsea actuators can be used for the pin actuation of these platforms. And moving on next is we're looking at the manipulators for the ROVs. So we at Maxon don't manufacture manipulators, but we do have products used in manipulators. So traditionally, the manipulators have been hydraulically powered, which means that on the ROV you've got to have a hydraulic tank of oil and the hydraulic motors to provide the sort of the power and pumps and things like that. So hydraulics has been known for many years to be quite dirty. It can leak. It's maintenance heavy. So there is a push to move away from hydraulics in this environment. So we have been involved with sort of providing motors for manipulator arms. So you've got on the arms you've got multiple joints. So you've got the elbow joints to where just like the elbows on the human. But then we also need to rotate those arms as well. So you're often getting multiple motors side by side in these arms. So what the customers need is they need high power density. So what do I mean by high power density? They want a lot of power, a lot of torque in a small package. And so we at Maxon, we're one of the world leaders in high power density DC motors. So our product line is ideally suited for these. So there's along with the joints as well. There's the grippers. They require actuation as well. So, but for the people who are using these, they are clean. There's no hydraulic leaks, and the maintenance is much easier as well. So it's a much better life for the customers and easy for them to use. And before I just get on to questions, there's just there's a few more areas as well where our products are used in the subsea arena. So we are used in there's been systems of hull cleaning on ships. So we've had motors on that kind of product, and then also aquaculture and and the fishery industry as well. These are relatively low. So they don't go to the same depth, so they're not as challenging as some of the other applications that we've been talking about. But we are involved in those areas.
Okay. Thank you very much, Andrew. Just a quick question, really. It's just to get an idea of the products that you're talking about here. They have been specifically designed for these applications, or are they taking from areas that Maxon's worked in before and adapting technology?
No, these have been specifically designed for this arena, because of the challenges of the pressure. It's the motors inside are very much based on sort of the standard motors that we do. So it's how we package them, and then bringing in the material changes, the pressure compensation as well to make them operate in this really challenging environment.
Okay. And just to get an idea of the market, is this a growing market at the moment?
It's growing for us. I mean, it is a well-established market. There is a push to change away from hydraulics to more electric. Now, a lot of the ROVs, we'll be the first to put our hands up and say they're way too big to use our thrusters and our motors in the manipulators. When we're looking at sort of some of the ROVs, the huge, they're 2 meters high, 4 meters long, 3 meters wide. They're really big, sort of big products, and our product is just way too small. So although we've got these products, it is quite a niche area in the field that our products are suited to.
Okay, I'm afraid that's all we have time for today. But as I mentioned earlier, if anybody has any questions that haven't been answered, we will hand those on to Maxon and have them answer them offline. And with that, it just remains for me to say thank you very much to you, Andrew, and to all our audience for joining us today. Thank you very much.
Thank you, Paul.